Hello, I'm Jason, and I'll be discussing the effectivity of lenses, prisms, their optical concepts, and their clinical applications. First, lens effectivity is the change in divergence of light that occurs at different points along its path. The formula for two lenses of powers f1 and f2 is given by f2 equals f1 over 1 minus d times f1, where f2 is the difference in f1 and the displacement of a lens d in meters. D is positive when moving towards the eye and negative when moving away. Two lenses are said to have the same effective power if they both form an image on the far point of the eye, the retina. When prescribing a distance correction, the principal focal point f2 of the correcting lens must coincide with the retina. We must also consider the vertex distance, as it affects lens power in higher ametropias. Glasses usually sit about 12 mm in front of the cornea. The closer to the eye the lens is mounted, the shorter its focal length in the case of hyperopia, and the longer its focal length in the case of myopia. Lens effectivity is important to consider when changing the vertex position, such as converting from glasses to contact lenses. For example, we have a myope who wants contacts and was refracted at 12 mm, resulting in a -4 diopter prescription. Using our lens effectivity formula, we can see that f2 equals f1 over 1 minus df1. We can plug in our numbers in to see that a -4 diopter lens is equivalent to a -4.2 diopter contact lens. In low power lenses, lens effectivity is not clinically significant. However, if we were using lenses with a power of greater than 4 diopters, we can use a vertex conversion chart to help us to do these calculations quickly. Just remember, cap, the closer you get, add plus. Intraocular lens insertion was a big step in cataract surgery, as aphakic patients used to end up with very significant prescriptions and aberrations. These IOL formulae were originally derived from the lens effectivity formula. It enables us to calculate the required IOL power in relation to the corneal refractive power, effective lens position, and axial length. Now, over to prisms. A prism is a transparent optical element bounded by two plane surfaces which are inclined at an apical angle. This is the apex and this is the base. Incident rays passing through are deviated towards the base of the prism, and the net change in direction from the original path is called the angle of deviation. Therefore, the virtual image projected to the eye is perceived like this, shifted towards the apex. The power of a prism depends on, number 1, the refractive index of the substance of the prism, number 2, the apical angle, and number 3, the manner of incidence of rays, i.e. the position. This is why we have standard positions for holding prisms. For glass prisms, we use the Prentice position. The line of sight makes a right angle with one of the surfaces. For acrylic prisms, we use the minimum deviation position. The line of sight makes an equal angle with each prism surface. Clinically, however, these prisms have been held in the frontal plane position, which approximates the minimum deviation position. In ophthalmology, we use low power prisms, and our primary unit of measure is the prism diopter, which describes the number of centimeters of deviation at 1 meter away, indicated by delta. Clinical applications for prisms include the assessment of ocular deviations. We use the prism cross-cover test and the prism cover-uncover test to measure all varieties of strabismus. Prisms are orientated according to their base and, in strabismus, should point in the direction of the deviation. Base out for an esotropia, base in for an exotropia, base down for a hypertropia, and base up for a hypotropia. For example, in a left esotropia, we neutralize it by holding the prism base in, shifting the image towards the fovea, and can then calculate how many prism diopters were needed until this null point. Prisms are also used therapeutically in glasses, such as these Fresnel prisms, in which a cross-sectional view shows us how the angled surface is broken up into a series of much smaller prismatic surfaces at the same angle. Finally, prisms are utilized in ophthalmic instruments such as the binocular ophthalmoscope for their ability to exhibit total internal reflection. In the binocular viewing system, light exceeding the critical angle is deviated 90 degrees, twice, to reach the observer's eyes, which are much further apart than the incident light. This property is also seen in applanation tonometry, where two prisms in opposite directions deviate the upper and lower half of the mires, which then have to be aligned like this, representing the point at which a 3.06mm diameter surface of the cornea is flattened and can measure the required force.